In a previous video, I went over the math behind the Fast Multipole Method, or FMM, a legendary algorithm which gives a blazingly fast, and most importantly, accurate approximation of the n-body problem in ON, allowing us to run these types of gravity simulations you see here. Now I'll describe my implementation of the algorithm and do some performance tests, to see how much of an improvement it is over brute force calculation, as well as the more commonly seen Barnes-Hut algorithm, as well as verify its accuracy. I'm going to give a very brief summary of FMM now, but if you haven't seen the first algorithm video, be sure to check it out. So I explained the algorithm in a pure 2D universe, and used that as justification for using a gravity that obeyed an inverse law instead of an inverse square law like the universe we live in. This caused quite the stir in the comments, so I'll start by addressing that. It's very possible to write an algorithm that works in 3D, using the usual law of gravity, so to speak. The purpose of the video was to showcase how the algorithm worked, and 2D is just the simplest version of that. If you want to learn how the 3D version works, then get ready for some spherical harmonics. I've linked the paper down below. The algorithm works by considering two expansions, both formed with Taylor series. The first is the multipole expansion, which represents a cluster's influence on faraway regions. The second is a local expansion, which represents the influence of many faraway multipole expansions onto a local region. The number of terms in these expansions is called p, and the higher p is, the more accurate these approximations will be, and we can bound the error in these approximations to be exponentially decreasing with p. What's more, we can work out mathematical operations to shift the centers of both expansions, as well as flip a multipole expansion over to a local expansion. This allows us to compute the effects between clusters directly. We can define clusters by creating a hierarchical structure known as a quadtree, and through an intricate sequence of shifts, flips, and other expansion interactions, we're able to bound the number of operations per box and per particle to a constant, resulting in a linear O(n) runtime. And now let's begin. We'll be using the old combo of C++ and SFML for rendering. To be honest, I didn't really know how to start writing this algorithm down. There are a lot of parts, and I'm still relatively new to this sort of thing. But we can break this problem down into 5 main files. First, we need to construct the structure that stores our particles, the quadtree. Specifically, I'm implementing the version of FMM with an adaptive quadtree that changes with the distribution of particles, which is the most general version that should achieve O(n) across all particle distributions. This can also be used to implement the Barnes-Hut algorithm, which also requires a quadtree since we want to do comparisons. Second and third, we need to write files representing the multipole and local expansion, respectively. Fourth, we need something that uses these to implement the actual FMM algorithm. If you recall, the main steps are sorting the particles into the quadtree, performing an upwards pass to generate multiple expansions for each box, generating different interaction lists for each box to decide what contributes to its local expansion, performing a downwards pass to create local expansions for each box, and finally calculating the forces from the local expansion on individual particles. Last but not least, we need a master file that we can use to start our simulation and test different parameters. Let's start with the quadtree then. We need to define what a source or particle is, so we can give it a position, a velocity, and a charge or mass, and then some constructors. Next, we need a struct for each tree node. I wrote a basic node that serves as a template upon which we can add other stuff. We're going to have it store the center of the box, its length, its level, and whether it's a leaf of the tree to help us during traversal. Moreover, we need to store a node's parent and its children, so we can actually traverse. Initially, I did this using pointers, but to make this more optimized, I decided to use a memory pool to pre-allocate a contiguous block of memory for our tree nodes, to remove the time the computer spends allocating memory and making our code more cache-friendly. This allows us to simply store the indices of other nodes instead of pointers, and also made my tree creation much faster. It'll also be better for multi-threading in the future. Lastly, we have a function to tell us whether two boxes are touching, which will be used in generating our interaction lists. Before we get to that, we should define the rest of our base quadtree class. Apart from the memory pool, we have some basic stuff like the height and this helper array to move towards our child nodes. To calculate how big our initial node needs to be, we need to know the range that our particles spread over, so here's a function for that. Also, as a debugging measure, I added this breadth first search function that traverses the tree and allows us to perform some process on each node, say check its size or position. Now that our base quadtree is done, we can move on to our FMM specific code, in particular the two series expansions. I wrote a base class storing its center, its order aka number of coefficients, and an array of actual coefficients. If you remember back to the algorithm, calculating new coefficients for shifting and transforming these series includes some binomial coefficients, so I also made a helper struct for that, which we can pre-calculate when the series is initialized to reduce the amount of work we need to do. Then, in the rest of the base class, we have an operation for adding the coefficients of two series, accessing coefficients of the series, and placeholder functions for evaluating either gravitational potential or force. I lied about only having 5 files in the beginning. This goes in a 6th file of math utilities. Anyways, we can write out our multipole expansion class, which inherits from the series expansion class we just wrote. As you'll find out later, all the sources of one node will be stored in a contiguous block in a vector, so to calculate the coefficients using the formula we derived, we can give it just a start and end iterator of that vector and let it loop through the particles. It captures the faraway influence of a cluster on source targets. Moreover, we can write our shift operation for a single expansion using the formulas we derived. Then we can write a compound shift function to do this shift for an entire array of multipole expansions and combine all of them. Lastly, we can write functions to evaluate the multipole expansion to find the potential, as well as find the force as a complex number, which we figured out how to get after calculating the derivative of the potential. To be extra efficient, I used Horner's method, which is a neat trick for evaluating polynomials, or Lorentz series in this case. The way it works is through this recursive factorization. In the end, instead of calculating a bunch of powers, we just have p additions and p multiplications. This can also be applied to the force evaluation. A similar local expansion class can be written, which can be constructed from a list of particles, be shifted, and also have potential and force evaluated. The local expansion captures the influence of faraway source particles onto a local region, so more importantly, we have this function that takes a multipole expansion and transforms it into a local expansion. Then there's this constructor to do it for many multipole expansions and add up the coefficients. We're blazing through this. With our 2 expansions ready, it's finally time to start putting particles into our tree and doing stuff with them. After creating our initial bounding box and setting it as the root node, I took the most obvious option, the only option I knew of really, which was this classic recursive sort tree function. With a node and a list of particles, it figures out which quadrant each particle belongs to, copies them into 4 brand new vectors for the children, and then recursively goes down the tree. Pretty easy to understand, but it's an absolute performance disaster. Of course, I first swapped this out to use indices, like I mentioned before. But the main problem here is that the CPU constantly is allocating and deallocating memory in these vectors, with the particles in each node stored all over the place, making it not super cache friendly. Instead, I found a technique called in-place partitioning, which is basically the idea from quicksort. Since we have all our particles in one container, why don't we sort them so that each node's particles are in one contiguous block? This skips all the heap allocation and maximizes cache locality, and works especially well with our indexed setup. Now, instead of storing a whole vector of duplicate particles, each node can simply store 2 integers, an index for the first particle in the global list and the number of particles it contains. If you have some experience with this, the alarm bells should be ringing. This tree creation is still O n log n, not O n. The very first step is breaking the time complexity. And to that I have 3 responses. The first is that the algorithm is O of n practically, as the tree creation is pretty fast compared to doing all that math that the effect of it gets lost. I'm actually interested in what would happen if you create the tree not every frame but once every few frames, and see how that would affect the accuracy, while massively improving the speed. I'll probably report back in the comments, but you can go try that yourself if you want. The code is linked. My second response is that the authors use the technicality of how computers work to skirt around this. Computers have limited precision, so after a certain depth of subdivision in our quadtree, the box will be so small that we won't be able to tell 2 particles in the same box apart. So technically, the height is still bounded by a constant. If both these reasons weren't satisfying enough for you, my final reason for its use is arguably the more important advantage of FMM, which is its accuracy, as you will find out later. After that small tangent, we can create the 4 lists for each target box or node, again with a recursive function that processes nodes from largest to smallest. That's probably the hardest part of the code, so if you didn't quite get it the first time, I didn't either. So go back to the previous video and review the definitions and keep running through it until it makes sense. After creating the 4 lists for each node, we can begin our upwards pass, which forms multiple expansions on each layer, either directly from the particles if we have a leaf node, or from the 4 multiple expansions of child limbs. There's not really much more to say here, we just go from the bottom layer up, and do exactly what I just said. The more interesting pass is the downward one, where we do a bunch of things determined by the node lists we created to form local expansions. Firstly, we flip the multipole expansions of the nodes in the interaction list V to add to the local expansion. Next, we create additional local expansions caused by the particles in list X directly, ignoring the multipole expansions, since the boxes are too close to flip them over. Lastly, we take the parent local expansion, if it exists, and shift it down to the target. That concludes our downwards pass. But what about lists U and W? If we look at the algorithm, they don't actually produce local expansions, and so I added them to the final stage of evaluating forces. Firstly, for each particle, we evaluate the force caused by the local expansion of its box. Next, we evaluate the force caused by the boxes of list W using their individual multipole expansions, which were too close to flip over. Lastly, we deal with list U, the near neighbors, and other particles inside each box by calculating the forces directly, since they're so close we can't use any expansion. We're done. Let's test the speed on this thing with 50,000 particles and at most 100 particles per box. 10,000 of them uniformly generated in a square, with the additional 40,000 normally distributed in a circle. That's way too slow, and it's not gonna cut it for 60 FPS. But behold my secret weapon, multi-threading. Let's decorate our code with some OpenMP directives, and make some more changes to work with that. Wow, at 50,000 particles, that's still a far cry from 60 FPS. Thankfully, I was simply running the code very wrong instead of having any problem with the actual code. It turns out that I was in debug mode, which inserts tons of safety checks into everything and makes things slow. All we have to do is switch into release mode, and the simulation is up and running. Lastly, let's do some tests to observe the performance of this algorithm and whether it really holds up to the OVN standard. Firstly, we need to find our optimal number of particles per box limit, S. In the original paper, S is shown to not affect accuracy at all, just performance. So let's go in increments of 10, testing on 90,000 normally distributed particles plus 30,000 uniformly distributed particles, taking the average time spent for frame for 30 seconds, or 1,800 frames. That's a pretty nice looking plot. Looking at the original paper's analysis, the time complexity should be written in terms of S like the following, so let's do a regression. It looks pretty accurate to me, suggesting our optimal value of S is just about 60. Nice. To make sure that this works across any particle distribution, let's switch things around with 30,000 normally distributed particles and 90,000 uniformly distributed particles. It looks like it's not too far off, so we'll just keep 60 as a nice middle ground. For the next test, let's see how adjusting the number of terms in the expansion P affects the performance, with 90k normally distributed and 30k uniformly distributed particles. Since we've chosen our S parameter optimally, we should be expecting a quadratic curve, and that is indeed exactly what we get. The model is so uncannily accurate to our results that it's kind of insane. Next, let's test how the distribution of particles affects the runtime, keeping the total number of particles at 120k and varying the number of normally distributed particles in increments of 10k. It stays pretty stable, but there is a noticeable increase in runtime with more non-uniform distributions. What's very interesting is that the plot kind of has these three distinct levels of growth. My theory is that this may be because as the distribution of particles becomes more and more non-uniform, it reaches new density thresholds that mean we gain extra levels in our quadtree. Something like the load balancing of threads is probably also linked to the increase. That's something you can try for later. It's cool how these things emerge, and I have no idea why. Our last two tests will be comparisons with Barnes Hut. Firstly, the runtime graphs, where we can finally see if FMM is OVN or not. We'll be keeping normally distributed and uniformly distributed particles in a 3:1 ratio, all the way to 200,000 particles. And drumroll please. I think that looks pretty linear. Sure, in the beginning, since FMM is such a heavy algorithm, we have to deal with the effects of lots of direct near-neighbor calculations and a quick increase in the number of tree levels, but in the second half, it tapers off extremely nicely. If we apply a line, we see that it goes a bit above the origin, but I'm passing that off for overhead. Actually, we can see that there are kind of two lines in the latter part, and this could perhaps be the effect of the data spilling into a higher and slower cache level. If someone wants to do the calculations and verify that, be my guest. I have a very minimal grasp of hardware things. Finally, the accuracy of FMM versus Barnes Hut. At each frame, we sample 1,000 particles at random positions and can measure errors in two ways by comparing to the naive method of computing forces exactly. Firstly, we can just look at the magnitude between the exact and approximated vector to get an absolute error, and take the average of that. We can also look at the L-squared error, which is the square root of the sum of squares of absolute errors over the sum of squares of the exact magnitude. Since direct calculations of forces are expensive, we're going to cut the test down to using only 60,000 particles. First off, Barnes Hut, where we vary the theta parameter. Higher theta increases speed but reduces accuracy, and it's looking very bad. You can see the runtime shooting up as theta decreases, and it takes dropping below 40 FPS to get an L2 error of only 7.6%. And it only gets worse. Now, FMM. A second drumroll please. Bang! The error is perfectly exponentially decreasing with the number of terms we use in our expansions. With p equals 20, the L2 error is under 100 millionth of a percent. I can tell you my mind was blown seeing that for the first time, and I guess rip that one commenter that said people actually use the naive method in real life instead of FMM. I forgot to record the runtime for these FMM tests, but let's be generous and say when p equals 20, it was the same as when theta is equal to 0.5. Then we have an error nearly a billion times lower than Barnes Hut, which is simply insane to think about. If we choose parameters such that they both run at around 60 FPS, then the error is still over 1 million times better for FMM. I ran these tests after the first video, so it would have been really embarrassing if the error turned out to be not that much better, but these results certainly destroyed all my expectations. One last thing to think about. We managed to reach 140,000 particles running smoothly at 60 FPS, which is a bit more than the last video, because I did a little cleaning up of my code. So let's do the math. If we were to naively calculate all pairwise forces, how many forces is that per second? Well, we have 140,000 particles times 139,999 other particles that exert force times 60 frames per second. Over 1 trillion forces per second. The Fast Multipole Method, ladies and gentlemen. Thank you for watching, I hope you enjoyed. Subscribe. If you wanted to implement FMM, you don't really need to know where these formulas came from. The only problem is that, for me, FMM was way too interesting to not want to learn about. As a high school student myself, after understanding all this, it doesn't feel hard, but the thing is, nearly everyone gets their foundations through memorizing formulas and repetitive procedures, and nowadays AI. So they might think they understand Taylor series and complex numbers, but they'd be hard-pressed to intuit their way through that FMM video. That's why in this video, I'm excited to partner with Brilliant, an interactive learning platform built for students grade 5 to college, so if that's you or anyone you know, you definitely should go and check it out. Brilliant recently introduced their new tutor, Koji, and in their newly revamped math and CS courses, I noticed how Koji never reveals the answer, instead hinting students through the reasoning itself.
Good thinking. To narrow it down, what does y equal when x equals 0?
Being combined into the Brilliant courses means Koji knows exactly what you're learning and how it fits into the other modules, and can draw directly on the screen to show you what you're missing. Clicking into a random course and asking Koji some questions literally taught me something new. So if you want to try everything Brilliant has to offer, click the link below or scan the QR code on screen to try Brilliant for free, and also get 20% off an annual subscription at brilliant.org/keyframecodes. Thanks to Brilliant for sponsoring this video, and thank you all once again for watching.